All right. We're doing the Kalman filter, continuing with it. So last time we looked at the motivation behind the Kalman filter. And then from our motivating perspective, we derived a more general model. When with that general model, we proposed a linear filtering structure. And based on the intuition of what our motivating problem was, what our generalized model looked like, and what the structure of the filter was, we not really proved, we intuited what the Kalman gain should look like to weight the measurement error versus the, or rather prediction error versus the propagation when you're trying to fuse multiple measurements and predictions together. All right. We then phrased the problem as a maximum a posteriori estimation problem. All right. We quantified our uncertainties. I defined this error covariance matrix. We defined some terminology as well for the mathematical underpinning of what's going on here. And if you need to, you might want to go back and take a screenshot of this for reference as we go through the derivation. Yeah. And also of these two guys here. And yeah, and we developed what a process model was, that is how we transition from one underlying state to another, what our measurement model is, so how we get the measurements from that underlying state, how they relate. All right. Yeah, and then we re-solidified our problem as a maximum a posteriori estimation. And from that, we obtained this objective function. All right, so here I have this least squares objective function, which is good. I'm very comfortable with least squares. I like it a lot because usually it gives me an analytic solution when I try to optimize it, as long as the model I'm dealing with is linear. So what I want to do is linearize this measurement model about this this prediction of the underlying state at time t, given the information available at time t. All right. All right. I mentioned I liked the least squares function, and I mentioned that I wanted to make this measurement model linear in terms of the quantity over which we are trying to optimize. This one already is, the second term already is linear in the quantity over which we're trying to optimize. So I'm not worried about that. This here is G. We're going to do a little expansion. If you're familiar with state space modeling, all I'm going to be doing here is finding some approximation for the measurement model, wherein Z at time t is approximately some linear function of X at time t, right? Linear and without a bias term. What I'm about to do is show by Taylor expansion that you can also look at a Jacobian matrix to try to obtain that C, even in a nonlinear problem. But in general, we're just looking for some state space model where a measurement is some function of the error here. So this is what we're going to end up doing. So if this helps you remember, all we're going to be doing is saying Z hat is approximately equal to some matrix times X hat. That's the idea. Cool. So true underlying state is equal to some function of X, right? We can use a Taylor expansion and approximate this around some reference Z, right? So Z reference be equal to G of X reference. Cool. Plus the first order term, evaluated at whatever the reference X is, multiplied by how far away from the reference X actually goes, right? Plus higher order terms, which are the higher order derivatives of this function. Cool. Cool. Right. So we'll get Z minus Z reference. It's approximately this Jacobian matrix. Well, not great with handwriting. Times the deviation away. from this reference point. Cool. All right, now let's say we let X reference equal quantity we're trying to optimize, this guy in here. That means G, Z reference is equal to G, T, X reference. I dropped the T here. It can still be there. The reason I dropped it was to try to help keep the notation a little cleaner, so that if you go back and look at your notes, it's not just too overwhelming. Any individual part isn't too overwhelming. All right, cool. So this reference here is going to be the term that we have up in the objective function, right? Some sensitivity to the state evaluated with the parameter we're trying to optimize minus B. Cool. 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 So you see this term down here, this guy, it's going to be this term that we have up here. And put the t's back on, evaluating this at time t, and we're evaluating this at time t. Cool. So what we have is the idea that we can approximate this term in here, this function, by some matrix out here times a quantity in here, right? You may say, we have no idea what x of t is. The entire point of this problem is to try to find what x of t is. Well, x of t, given all the information at time t, is going to be very close to the true underlying state. That's what we're trying to do. We're trying to find this, like, we're trying to make this as close as possible. I don't need to obfuscate it with unnecessary mathematical lingo, even though I like mathematical lingo. It's not always helpful to everyone. So we're trying to get this as close as possible to xt, right? So when we're looking at this linear approximation, it's going to be perfectly accurate when we get to this point. So when we do this, do x t minus some change here as we distribute this matrix through x. I'm going to argue that by defining some reference coordinate system for z, we can just say that this quantity optimizing over this is going to be equivalent to just taking this difference, t times x. Apologies. This, yeah, this needs to be the estimated state. Cool. So we can, again, go back and see that perhaps an easier way to look at it that doesn't rely on a Taylor expansion is just say, I'm going to approximate my measurement model by this linear function here. And then I'm going to come through and I'm going to say my actual measurement minus my prediction can be replaced by some linear approximation, right? That's what we're going to do. So I'm going to define this matrix, camera, this matrix C is going to be the linear matrix that approximates this measurement function. Also here referred to as an emission function. Cool. So I'll call this at time t. Yeah, that's what we're doing. All right, cool. Let's plug this back into the objective function. And then we'll have a least squares objective function that is linear, that has models that are linear in the parameter over which we're trying to optimize. So this is the least squares portion. And again, perhaps you're getting sick of me emphasizing this. I want it to be linear in term, each term in here to be linear in terms of the estimate for X at time T, given the information available at time T. The reason I want that is I want a simple closed form solution for the optimal estimate for the underlying state. Cool. All right, we're back. Now we got this function that we can optimize. How? If you're not immediately sure, pause the video and think about it. But I'm going to optimize it by taking the partial derivative of this objective function. I'll call, I should have named it J somewhere, but I'll call this J, the objective function. Let's just call it objective. So it's not too confusing. If you look back at the notes, you think to yourself, where did J come from? Who is J? All right. We will be getting to this in a second. You may notice, maybe you can do it. I can't quite do this off the top of my head. I'm going to expand these terms. I'll be back in a second. I'm going to expand terms so I can get a function that's a little easier to take partial derivatives of. Okay, we're back. I expanded this term, these terms. And remember your transpose multiplication rules. You're not familiar with those if you're not sure how I ended up with, for example, this on the outside. Well, number one, good, because I missed a transpose there. And number two, you swap order when you're multiplying transposes. Yeah. It might be good for you to also go through and do this for yourself step by step as we go through here, because I'm almost certainly going to miss transposes here and there. I'll have to go back and correct them. Almost certainly going to miss some signs as we go through here. All right. So like I said before, we're going to optimize this objective function over the parameter we are trying to estimate. We're setting it equal to 0 because we're looking for a stationary point. And in this case, because it is quadratic, a quadratic optimization function, the models are linear in the terms over which we're trying to optimize. We are going to have a nice, easy convex optimization problem, so I don't have to worry about the optimum being on boundaries of the objective function of the parameter space, right? It's just a higher dimensional quadratic. Cool. So now we're just taking derivatives. These terms don't have any estimates in them, so be negative. So we'll put out the 1/2. And we'll have negative ZT transpose RT inverse CT. Cool. Then we'll have another one of those. ZT. You may think to yourself, why do I not transpose this? Well, think to yourself again, this is a covariance matrix, right? If it's a covariance matrix, it is necessarily some estimate of second order dispersion of a function, right? So they'll have some quantity. I believe this is sensor covariance. Yeah, the measurement covariance of the sensor. So it's ZT minus expectation of yes, that's right. ZT minus expectation of Z, right? So it's going to be symmetric necessarily. So I don't have to worry about transposes with those. Thank God. One fewer item to worry about messing up, right? So let's go back and restore all the transposes here. Cool. So this needs to be transposed. This guy does not transposed. Cool. All right. This one, differentiate it with respect to this one. Good. Parameter we're looking for. You can fast forward through this. I'm just expanding terms. All right. Remember your transpose rules here. It's more of a note to self. Gotta remember to transpose things. CT. Cool. Cool. And then we're down to the second line. And by now you can probably see a pattern starting to emerge, whereby we're going to have terms doubling up, which are then going to be canceled out by the 1/2. But since we're optimizing, setting this equal to 0, doubling up doesn't matter either, even if there wasn't a 1/2. It's just a scalar. All right, cool. And I'll put a times 2, because we're going to get that again. And we're going to get minus xt t minus 1 transpose. And remember, this sigma matrix here is going to be the error covariance matrix. It's a covariance matrix, so it too will be symmetric. And I believe we're going to get another one of these bad boys. All right, yep, times 2. And then plus x transpose t. Cool. Times 2. And if you don't know where those times 2's came from, go do it yourself. You'll see that you'll get double up terms like these in all the other terms of the objective function. All right, cool. So I'm going to consolidate some terms now. And yeah, you got the fast forward button if you need it. This, yeah, it'll be fine. It'll be fine. CT plus x goes and then get I'm I don't know what happened to that. T minus 1. All right, cool. T minus 1. And do those cancel? I think I might be missing a sign there. Hold on, let me check. I'm so sorry. I was so busy eating glue that I treated this guy over here like it's a term we're looking to optimize over. That is what? If you're not sure what this means, go remind yourself. This is the prediction for the underlying state at time t using the information we have at time t minus 1. This is a parameter we just already have. So we don't get this. That's simply not there because it does not depend on our estimate for the state at time t using all the information we have at time t. That goes away. Sorry. Apologies if you were screaming at the screen. Actually, if you're screaming at the screen, you probably just like being angry. So I don't apologize for that. You're welcome for that. All right. I'm gonna make sure there's not too many other silly mistakes. All right, cool. Looks like we're on the right track. All right, we'll bring this last term down into here. I've got a set of notes that I posted in the Slack for this. If you want to go look at it all ahead of time, pick out points where I'm making mistakes based on even my own work. But I highly suggest you just follow along, do it for yourself. It'll help solidify what's going on. All right, cool. So we have this equation, and we're now just going to solve it for this parameter that we're trying to estimate. All right, cool. So we'll have x t transpose times this quantity t minus 1. What is happening to whiteboard? Microsoft products, when you try to use them, it's designed for one purpose, and it cannot serve it. I suppose I should simply copy and paste these. I don't know, kind of like the feeling of writing out terms. And gives you time if you're trying to follow along at a normal speed. Again, you're probably just fast forwarding through parts, pausing it and doing it on your own, which is good. All right. So what I'm going to do is I'm going to transpose both sides so I can get a nice argument in here. So I can get this on the right-hand side. I think the transpose is equal to the transpose here. Now, when you're going through and I transpose this term in brackets here, it's going to happen. What happens to this term? 1 second answer. Nothing. Everything in here is symmetric. This is a symmetric matrix, the symmetric operation applied to it, and this is a symmetric matrix. It's all symmetric. All right, cool. This, however, is a vector. So what we're going to get is this term down here. Equal to these guys all transposed. All right. T transpose. The ZT transpose. ZD. There is a transpose here that I'm missing. Again, many benefits to doing this for yourself and following along, such as being able to immediately catch that. Yeah, a lot of those errors will come out in the wash, though. You'll realize the dimensions don't match up. And you need to get some vector quantity. All right, cool. Not a column vector quantity in this case. Right. All right. Cool. I think that's all correctly transposed. Take a peek at that. Yeah, that doesn't look correctly transposed for the Z. I'm gonna bet 99%. I forget. Yeah, cool. Got a transpose there too. Awesome. Transpose. 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 No. So cool. All right. Awesome. Promise I've done this before. Yeah, I've got the notes. Got the notes up on the Slack. All right, cool. And so now I'm going to argue we just invert this onto the other side. Well, invert it. Pre-multiply the inverse of this quantity on both sides, right? You may say, how do we know it's invertible? Well, this guy has to be invertible. This guy has to be invertible, right? And unless we come up with a pathological case for this quantity, the uncertainty matrix for our covariance of error is going to be non-degenerate, right? So we'll probably not have a direction in which we are perfectly certain of our estimate. So what it would look like if the sigma matrix was determinant 0 would be, we have this cloud here. We have a 3-dimensional position we're trying to estimate, and we have some uncertainty in X and Y, but not in Z. So our covariance just forms an ellipse embedded in 3D. But in that case, just don't bother estimating Z, because apparently you know it perfectly. Why do you need this math to estimate it if you already know it, right? So we, in general, we're pretty well assured we're going to have some finite volume contained within the uncertainty ellipse. Cool. Finite volume. Yeah. Pretty sure zero. Non-zero volume. Right. So we're going to have some uncertainty in every direction. That'll make this a nice rich matrix. Cool. If you didn't quite follow that, you can go look at debriefing 1, where I review the notion of determinants and linear algebra as something you can visualize. Determinants are volumes, matrices, even non-square matrices. You can visualize some volume that their columns contain in a parallelepiped, and that is interchangeable with the notion of determinant, though the determinant is only defined for square matrices. Anyway, I'm digressing. I'm inverting a matrix. All right, cool. And we'll down here, Great, copy and paste this. Don't need to rewrite everything, right? Copy, paste. Please fast forward. Please fast forward to this as I struggle with Microsoft products. Inverse. And R. And there we are. So, all right, cool. So let's check my notes here. Does that look good? Dimensions look like they match up. Mm-hmm. I hope so. All right. So we have Z here is going to be some Z dimensional vector. This will be a Z dimensional by Z dimensional matrix. This will be a X dimensional by Z dimensional matrix. So that means we'll have X dim by Z dim times Z dim times Z dim times Z dim by 1, which is X dimensional, which is good. That's what we're looking for. This will be X by X, and this is X by 1, so we're good there. And let's see. Same argument to this term and same argument to that term. Did I appear to have copied and pasted the wrong things. Don't know how I managed that. Did I forget to click the copy button correctly? There is caramba. Right, so this thing is supposed to be inverted onto the other side. I don't know how you got here. I don't know how you got here. No wonder it was so long. It was the wrong thing. Apologies. Right? We're pre-multiplying the inverse of this on both sides. This quantity. All right, cool. Cool. Yeah, so this will be X dimensional by X dimensional. This will be X dimensional by X dimensional. Cool. Cool. So we have a nice expression. This is a place you could stop if you wanted to. If you have a really strong computer, you could stop here. The issue is, you may note this doesn't really look like what we were setting out to obtain. I was promising you some filter that looks like a linearly weighted trade-off between our error in prediction and our previous estimate. And you can, in fact, get the Kalman gain out of here, out of this final expression we just obtained. However, you'll notice we invert two matrices only to invert it again. And you may intuitively think, it seems like we can make that simpler. This seems unnecessarily complicated. And you'd be right. But to do that, we're going to get into a little bit of matrix math that almost every guide that I find just keeps skipping. It's called the Woodbury matrix identity. And it's not that complex. It's just kind of a long walk. So assure yourself that you follow with what's going on up to this point. And then we'll do a matrix identity to make this term easier. And we'll get the linear filter we're looking for. Cool. All right, cool. So we're going to start with the X cathedra Woodbury matrix identity. The idea is we have some set of matrices where A and D are square and invertible. And we can expand this a term of this form into this form, right? And we'll use it to eliminate some of the complexity in this and obtain the Kalman gain as a single term. I got this specific way of going about the proof from the T. Lennart blog. I liked his style. It was very succinctly posited. And it was one of the only places I saw it that wasn't just citing it somewhere else or getting it out of Matrix Cookbook and saying, this is the way it is. So the basic idea, in order to derive this seemingly complex identity for yourself, is to, number one, I'm sure there's some underlying intuition that I've missed. Number two is to visualize the matrix M as a matrix of blocks, right? So we'll have the A matrix, top left-hand corner, B matrix, top right, C, bottom left, D in the bottom right, okay? A is going to be n by n, B, C are going to be non-square, D is going to be m by m, right? So we'll have m, I shouldn't use capital M, I'm going to use it for the matrices. Call these n and m, little lowercase, just in case you're referencing this at some later date. Cool. So we have m of the shape that looks like this. So we have n by n. We don't necessarily have each of these blocks here square, m by m, right? So this bottom left here is going to have n columns and m rows. So it'll be m by n. And this over here will have to have n rows and m columns. So it'll be n by m. Really not good letters to say out loud. And I realize this now that I'm actually having to say them out loud, that having them in my notes like this was perhaps not the best call. Right. So we, just by matching shapes of how this matrix has to be stacked, we're going to get this. Cool. That is an M. You can see what's going on there. All right. So because we've loaded these diagonal with matrices A and D, we're going to say A and D are invertible. All right. That means M has to be invertible. All right. If you need a way to think about it, you know all the columns of A are going to be linearly independent, right? Down here, even if C is just random numbers or all zeros, these columns will still be linearly independent, right? The same will hold for the columns of D if D is invertible. And then we just add all the fluff on top of them, right? Because we've appended higher dimensions to all these, and because we know if we have all the fluff down here and all the span of D lies within entries down past dimension n, and all the span of A lies in dimension n. So we have valid entries for A in the vectors up here, and then nonsense below. And then for D, we'll have valid entries down here, or rather, entries that we are guaranteed to have span some space. And then stuff that may or may not actually contribute to spanning the space above, since we know that this is spanning in dimensions 1 through n. This is n through m. We know that this entire thing has to be full rank when we stack matrices on the block diagonal. Cool. So this matrices inverse exists. Neat. So I'll go ahead and name this guy as well. And Mr. Leonhardt recommends the notation W, X, Y, and Z. All right. These are block matrices as well. And so the goal here is to find some expression that relates all these A, B's, and C's together in terms of the inverses of A and D in a single equation. All right. So we're going to use the fact that M times M inverse is equal to the identity matrix, and that M inverse times M is equal to the identity matrix. But our overall goal will be to get rid of all these W's, X, Y's, and Z's when we finally have equations from these relationships in order to get a matrix identity that will tell us useful information about how A and D can be inverted. Cool. I'll erase this line in here. So M times M inverse is equal to this times this. Follow the basic rules of matrix multiplication in block form. And it's going to end up being the 0. It's going to have a smaller identity matrix, a 0 matrix, an identity matrix, right? Because an identity matrix is just a set of ones stacked along the diagonal. So we can break it into smaller identities whose dimensions are going to be n by n and m by m. All right. So we'll have AW plus BY. All right. CW plus DY. AX plus BZ. And CX plus DZ. Cool. Cool. Right. Sounds good. Cool. So we can write out these equations like this. This is equal to an identity matrix. It's W plus DY equal to 0 matrix. AX plus BZ. It's also equal to 0 matrix. CX plus DZ is equal to an identity matrix. All right, cool. So we're kind of sprinting backwards here, but I wanted to show that this matrix identity is in fact valid. Sprinting backwards, we can see where we've been, but not necessarily where we're going, but we're going very fast, right? So sprinting backwards is the way I express that. All right, so we're going to multiply both sides by A inverse to get W plus A inverse BY. A inverse. All right. And we can do the same thing here to get D inverse CX plus Z is equal to D inverse. All right. The overall goal is a way to relate multiplication among the inverses of these terms, and not the inverses of these terms, but these off diagonal terms. Right. Okay. Right. All right. So now we have x and y in these equations, and we'll get rid of, nice spelling, get rid of x, y. There's our next goal. So to do so, we will look at these equations over here, recalling that only D and A are guaranteed to be invertible. We can look and see that x can be equal to negative A inverse BZ, and y is equal to negative D inverse CW. Cool. Am I right? All right. Cool. So leave now. I'm going to go ahead and plug these guys in to their respective terms and expand. And then we're going to look at a way to constrain W and X. Constrain W and Z. By X, I meant Z. We're going to substitute in expressions for X and Y, and then look at a way to constrain W and Z. Cool. We're back. W plus y, and then we'll have D inverse CW, right? And I need to change this to a negative sign. Negative. It's equal to A inverse. And take in this substitution here. And we'll have, where'd you go? There's the X. D inverse CX. C. A inverse. That doesn't look right. Looks like a term has fallen off somewhere. There should be a Z here. I don't know how that happened. Yep. Anyway, continuing. Substituting X into here. A, B, and Z. Z. All right, cool. So now we can post factor some terms. So we'll get an identity matrix minus A inverse B, D inverse C. This whole quantity times W. The A inverse, and a similar idea, but looking at Z, we'll have minus D inverse C, A inverse B, Z is equal to D inverse. Cool. All right. So now what we're going to do is we're going to take these terms over here. We're going to invert them on both sides. And then we're going to go back to these equations and look at the second set of these equations, which is just swapping the order of M and M inverse. And then with that, we'll get a set of constraints on what what W and Z can be. And from that, we will get the relations we're looking for. All right, cool. And if you're worried about the inversion, you can think of this as a regularizer with alpha 1. So if you remember pseudo-inverse regularization, this is sort of like a regularizer with alpha 1. So barring degenerate cases where this quantity comes out to be the identity matrix as well, we won't worry about the invertibility. And in general, when we're plugging into this relationship here, we'll see that the final matrices we get out are not going to be likely to cause inversion issues. All right, cool. So we're developing equations for W and Z. W is equal to this. I'm doing this in the right order. Yeah, pre-multiplication. Yeah, pre-multiplication. Good. So we'll take this term here. A lasso selected. Maybe save us some time. Lasso select them both next time. Yeah, cool. That's inverse on A here. Right? Cool. And I'll take this, copy, focus down here. And we invert that onto D inverse. And this is equal to Z. Cool. You may notice that this is an inverse times an inverse. So what we can do is argue that AB inverse is equal to B inverse, A inverse. All right. So we can transpose these and phrase this all as quantity inverse. That's the reasoning we're about to apply. All right, cool. So we have A times this quantity that I have just, man, I had only thought through a little bit more. I would have done this one at a time. All right, bring this down here. So we're going to get this quantity inverse. You may notice that I've copied and pasted the wrong thing again somehow. Did I not hit the copy Control C button? Perhaps Control C is not a valid selection for this. App. Maybe this is the first app in the world that doesn't have Control C. Yeah, there we go. That's what I'm looking for. All right, cool. Quantity inverse. The reason that I was suddenly very confused was I want to distribute this A through and eliminate this inverse here. See? So we're going to get A minus B D inverse C. Inverse. So you can see we're getting close to eliminating all these X, Y's, and Z's. We're going to do something similar here, where we're going to put down D. We'll have this quantity here. C, A versus B, right? Quantity inverse, which is going to get us D minus C inverse A inverse B, quantity inverse. Cool. Cool. So, like I said before, we're going to use some relationships derived from the fact that we can multiply a matrix and its inverse on either side in order to get one, in order to constrain what W and Z can be. And in doing so, we'll be able to relate terms like this to identities that help simplify them. All right. So like what we're looking for up here. All right, cool. All right, cool. So I've moved this equation down from above. This is the same idea. We did M times M inverse. Now we're doing M inverse times M, but it's still going to equal the identity matrix, right? What happened here? Why is this identity matrix back? I thought I had undone it. I think perhaps there is too much on this whiteboard and it is hurting Microsoft. Cool. So we're going to derive some equations for what the constraints on these M inverse terms will look like. All right. So we're going to get WA plus XC and then YA plus ZC, WB plus XD, and then YB plus ZD. Yep, there we are. It'll appear all at once. All right, cool. So WA plus XC equals identity, just like before. You can work through the reasoning on all this This isn't particularly challenging. In fact, there's an argument for simply double tapping that fast forward button to get through me writing out equations. All right, cool. So these are the equations we obtained from the reverse case. All right. So at this point, you may inspect these equations. They go up here. You may realize, hey, I can relate x to w here. I can relate x to z here. I got expressions for w and z. If I set the expressions for x equal to one another, because x is equal to itself, then I can just get rid of all these x, y, and z terms altogether. Cool. So what I'll do, I'm going to say x. Ooh, we going to write? You good? All right. Negative w, b, d inverse. Cool. From this equation. And then from above, we can also say it's equal to negative a inverse bz. So Ooh. Cool. So that means WBD is equal to A inverse. Here. Instead of saying it, just write it. I'm getting a little tired. Welcome to the joy of painting. Mathematical lectures do not benefit from Bob Ross' voice. Microsoft products are getting tired too. Just kind of gave up on writing it halfway through. Dropping frames. Right, so I'm substituting this term for W into here. BD inverse is equal to A inverse B times Z, which is right here. D minus C A inverse B, quantity inverted. Isn't that neat? All right, so gotten to here. I want this to write with a pen, please, not just click things. I want this term to cancel with something in this term, right? Because I want only this information for my identity, remember? So if we go back up to the goal here. Goal is to get an identity that describes how A, B, and C all go together, relating the inverses of A, D, and function of B and C to this expansion here, right? So this BD inverse on the right-hand side is just getting in the way. So let's go ahead and get it out of the way. How do we do that? So you can start by observing that there's something that looks awful lot like this term hidden inside the term it's being multiplied with. And that's a little hint that there might be something some trick we can do to have it cancel. All right. So I'll continue this. BD inverse C is, yeah, can be post multiplied by A inverse here. And that'll get us, I think that'll look like, well, get us. So if we take this term, the non-inverted term, post multiply by A inverse, we're going to see we can get some term that looks like this, right? And this is equal to the non-inverted term over here. So what we're going to do is strategically try to insert this non-inverted term in the hopes of expanding this and getting it to cancel. So we're only left with terms of this argument and its inverses in the left-hand side of the equation. So if we inject this term up into here, we'll be able to get a non-inverted term of this. But notice we're gonna have to post multiply both sides, right? B to inverse, C. Quantity inverse inverted. C inverse, A inverse, A inverse B, D, C, A inverse B, and the inverse, C, A inverse. Let's see where the formula is starting to come together just a little bit. So we're going to get this. This guy here, we can relate into here. B, D inverse, C, A inverse. With this quantity that we wanted to inject to get rid of this and to help everything cancel out so we only get terms in this argument. Rid of. You'll see what I mean. You'll see what I mean. In fact, you can probably pause it and do it yourself faster than I can. All right. So we have identity matrix minus A, B, D, C. All right. A inverse. Is it looking good to you? You agree with that line of reasoning? And check my signs, though. Check my signs. All right, cool. So we're going to distribute this term through these. I'm going to see we get the identity term. So we'll get this popping back up again. So yes, it remains, but you'll see it's going to cancel with this such that we've eliminated these B and D terms. All right, so minus identity matrix times A inverse. Good to you? Looks good to me. Equals, said equals. Sorry about the whiteboard. C A inverse B inverse C A inverse. Cool. Now let's go ahead and add the A inverse to the other side. So we have A inverse B D C equal to A inverse plus this whole mess of letters. All right. Now let's check if I got that right, because I think I got it. I think I got it. Let's go up to check this while it's paused. Ooh, did I get the minus signs? Come on. Come on, whiteboard. All right, cool. Good. Looks like I got the minus signs too. All right, cool. So this is the matrix identity we're going to be using to simplify Kalman gain in a second. Cool. See where it comes from? You see where it comes from by manipulation. Perhaps it's not intuitive, but you can reproduce it. You remember what these matrices all look like, right? So as long as we have invertible matrices for A and D, B and C just have to have dimensions that match A and D appropriately, right? So we can have an M by M D matrix, N by N A. So as long as I've got N by M and M by N for C and B, C and B can be anything. I'll go ahead and say, I know that for certain they can be anything real. I don't see a reason why they couldn't be complex off the top of my head. We'll have to study up on the inversion of a complex matrix, but in most cases, you'll be using real numbers anyway. Complex numbers and matrices don't really come up too often. One often can take the job of the other. All right, cool. So this is the identity we're going to apply next time in order to obtain the linear form of the Kalman gain. But this was my aside on the matrix identity that keeps coming up in textbooks, and they say, take it ex cathedra. That's where it comes from. And again, thank you, Mr. Liebert. Was it? Leinert. Leinert. Lienart. All right. I hope this has been useful, folks. Very, very good application of MAP estimation. If you're in this machine learning class and you're doing some sort of engineering, mechanical, or aerospace, any type of robotics do, you're going to end up in using something like a Kalman filter at least once in your career.